Welcome to the Explainer. You ever wonder how noise-canceling headphones just work? Or how a giant, complex song file gets squished down so it fits on your phone? Well, the secret sauce is a seriously powerful idea from math called the Fourier Series. Today, we're going to see how even the most complicated, messy signals are really just a bunch of simple waves playing together.
So let's start with a really big question that gets right to the heart of it. Think about the sound of a guitar string. It's rich, it's complex, it's got character. But what if I told you that we could perfectly rebuild that exact sound just by adding together a bunch of simple, pure tones? How in the world can you build something so complex from stuff that's so, well, simple?
The answer, you guessed it, is the Fourier Series. It's kind of like a mathematical prism. You shine a complex, repeating wave through it, like our sound wave, and out the other side comes all of its basic building blocks, a whole collection of simple, predictable sine and cosine waves. So here's how we're going to break it all down. First, we'll talk about the big idea, why simple waves are so powerful. Then we'll get our hands dirty and decode the master formula. After that, we'll run through two super important examples to see it in action, and we'll finish up with your own personal Fourier toolkit. Okay, let's jump in. Section 1. The power of simple waves. Before we get lost in the formulas, let's just sit with this for a second. Why are we so obsessed with sine and cosine waves? What's so special about them? Well, here's the thing. This isn't just some abstract math puzzle. As our source material points out, this is the standard way it's done in signal processing. This is the engine behind everything from cleaning up audio recordings to compressing images. The Fourier series isn't just cool, it's absolutely essential. All right, on to Section 2, decoding the master formula. We've talked about what it is and why we should care, so now let's get into the how. We're about to look under the hood at the engine that makes this whole thing run.
And there it is. Yeah, I know it looks a little intense, but think of it like a recipe. The fx on the left, that's the cake we want to bake. The sines and cosines, those are our ingredients, like flour and sugar. And all those little a and b coefficients, that's the recipe telling us how much of each ingredient to throw in the bowl. So how do we figure out those amounts? Let's start with the a coefficients, the ones for our cosine waves. We find each one using this integral. Here's a way to think about it. This formula is like a detector. It scans our original function to see how much a specific cosine wave is hiding inside it. The integral then just adds it all up and gives us one number, the strength of that cosine component.
And for the b coefficients, you guessed it, it's the exact same idea. This time, our detector is tuned to look for sine waves. It multiplies our function by a certain sine wave, and that integral tells us just how much of that sine wave we're going to need in our recipe.
Okay, now listen up, because this is super important. This slide points out two spots where it is incredibly easy to trip up. First, you've got to remember that 1 over L scaling factor out front. L is half the period of your function. Second, make sure your integral goes across the entire interval, from minus L all the way to L. Getting these two details right is absolutely crucial. Okay, that was a whole lot of theory. Let's make this real. Section 3, our first example, the sawtooth wave. We're going to put these formulas to the test, and in the process, we're going to find a really clever shortcut.
So our mission is to take this really simple function, f of x equals x, just a straight diagonal line, and break it down into its sine and cosine parts. A straight line doesn't really look like a wave at all, does it? So let's see what it's really made of.
Now here's where the magic happens. The very first thing you should always check for is symmetry. Our function, f of x equals x, is what we call an odd function. And because of that, something amazing happens. All of those a sub n cosine coefficients, they're all zero. Poof, gone. We don't even have to calculate a single one. We literally just saved ourselves half the work.
And that right there is a huge concept. The personality of the original function tells you exactly what ingredients you'll need. Since our sawtooth wave is an odd function, it can only be built from other odd functions. And in this case, that means it's made up entirely of sine waves.
So what happens when we don't have a neat little shortcut like that? Well, that brings us to Section 4 and our second example, a shifted pulse. This time, we're going to have to roll up our sleeves and use the full method.
Our function this time is just a simple little box. It's on for a bit, then it's off. But you'll notice it's not centered on the origin. It's been shifted over. Let's see what that does to our calculations.
So we look at this pulse, and yeah, it's not symmetrical at all. It's not even, and it's not odd. And you know what that means, right? No shortcuts. We have to do the whole shebang. We have to calculate that constant term, we have to calculate all the cosine A terms, and we have to calculate all the sine B terms.
So the final result is exactly what we'd expect. Because our original pulse didn't have any nice symmetry, its series is a full-blown mix of both sines and cosines, all working together to build that specific shifted shape.
All right. We've tackled the theory, we've walked through two really important examples. Let's boil it all down into our last section, your Fourier toolkit. These are the key things you need to remember every single time.
You know, putting our two examples right next to each other tells the whole story. The very first thing you should always do is check for symmetry. Seriously, it is the single biggest time saver there is.
This table just makes it crystal clear, doesn't it? For our odd sawtooth wave, the A terms just vanished, leaving us with a pure sine series. For the non-symmetrical pulse, we needed both A and B terms to get the job done. The symmetry dictates the entire recipe. It's as simple as that.
So here it is, your 4-step game plan. Number 1, check for symmetry first. Number 2, don't you dare forget that 1/L scaling factor. 3, integrate over the full interval from -L to L. And 4, put all the pieces together to build your final series.
And that's really the coolest part. You don't need to grind through dozens of examples. By really truly understanding just these two cases, one with a shortcut and one without, you've pretty much unlocked the logic for solving any full Fourier series problem they can throw at you.
At the end of the day, the Fourier series is way more than just a formula you need for a test. It's a whole new way of looking at the world. It lets you see the hidden simplicity hiding inside all the complexity around us. From the music you listen to the light from a star, it's all just waves. So I'll leave you with this question. What complex thing out there are you going to break down next?